emissions, which mostly stem from energy-intensive industries. And what's a very important milestone in Germany is that we have an interim target for the industry sector to reduce our greenhouse gas emissions by at least 57%, which are 118 million tons CO2 equivalent in 2030 that are left for the industry sector. And while we have this societal and political consensus on this target in Germany, the pathways we will take to achieve this target are really still very strongly under discussion. In addition to the already challenging transformation of the industry sector, we now face a new challenge because industry in Germany, 1/3 of the final energy demand is covered by natural gas demand today, plus the natural gas demand we need for feedstock uses. And in the light of the current crisis, we see that natural gas, which has been assigned a very central role in the transformation of the industry sector, is now really uncertain and called into question as a bridge for the industrial transformation. And this really poses additional challenges for the industry sector in Germany due to high gas, but also electricity prices. In our scenario analysis we do in the Copernicus project Ariadne, we normally try to gain knowledge by comparing different alternatives. So we looked at 5 scenarios in this project, but today I will only talk about 2, which are the mix and the energy sovereignty scenario, which are both climate neutrality scenarios. So in 2045, we want to achieve near climate neutrality in industry. In the mixed scenario, we have no clear technology focus. So this means that we mainly use technologies with a very high TRL in the sectors, or which are discussed as particularly promising. In the energy sovereignty scenario, which is the red one below, the scenario is characterized by a very strong loss of confidence in natural gas as a reliable source of energy. So the companies, especially in the short term, try to do everything to reduce their demand for natural gas. When we look at the overall scenario results, what you see here on the right-hand side is the industrial energy consumption for Germany, energetic and feedstock uses for the both scenarios. And in both scenarios, which is not surprising, we see that the industrial transformation really needs high amounts of CO2 neutral energy carriers. In red, you see the development of electricity. Blue is the future hydrogen demand. And depending on the scenario, we see that we achieve between 250 and 280 terawatt hours electricity demand for industry and between 200 and 300 terawatt hours of hydrogen demand in the industry. And that even though we already assume very ambitious improvement also in the area of material efficiency, circularity, and also changes in activity effects in the scenarios. What we see on the right-hand side in the energy sovereignty scenario, where we have this loss of confidence in natural gas, is that we will have a very strong reaction to the high natural gas price signals, which leads to a permanent decline in natural gas demand in this scenario, around 50% compared to today's level, which mostly takes place in the steam and hot water generation in industry. But what we also see in parallel is that we, without additional measures, have an evasive movement in this sector to, for example, more CO2 intensive energy carriers like oil, but also to a certain degree biomass, because electricity is not competitive without additional measures. To counteract this evasive movement, faster electrification of process heat, for example, using hybrid systems in the steam and water generation, but also maybe partial electrifications in the area of furnaces could help to counteract this short-term target conflict we see here with our long-term climate neutrality ambitions. What we see relatively robust throughout all scenarios we looked at, also the others I'm not showing today, is hydrogen demand in the steel production via direct reduction and also as a feedstock for the chemical industry. And this demand really is distributed among very few industrial locations. I think it's around 20 in Germany. If we would increase this demand up to the remaining process heat, we see here 60 additional terawatt hours of hydrogen demand in the scenario. And this demand would then be really require a large-scale expansion of the hydrogen distribution grid, especially the use of hydrogen or electricity in the remaining process heat really depends on sector-specific factors. Especially in the area of furnaces, they are very heterogeneous and require individual considerations. So what we see here is that there is still a certain degree of uncertainty for the remaining process heat via either the use of hydrogen or electricity. For the chemical industry, we see a certain challenge because in the decarbonized target system, new sustainable carbon sources need to be developed and are needed. And in our scenario, for example, where we assume that chemical production stays in Germany and will probably based on green hydrogen, we would need 30 million tons of CO2 demand to produce methanol and high-value chemicals via the MTO route. One way to provide this CO2, for example, could be to capture and use emissions from other industrial sectors, especially sectors that are very hard to decarbonize. In our case, this could be, for example, process-related CO2 emissions from the cement and lime industry, because these sectors are really hard to decarbonize at the moment. And why you see here that the potential and the demand, the potential sources and the potential demand would more or less add up in this scenario, there are still challenges, because to really address these potential sources and demands, you need a combined carbon management strategy. So here on the right-hand side, you see such a potential CO2 transport network that could be or should be developed in the case of Germany, which would be more than 5,000 kilometers of CO2 transport network, which could be partly generated by reusing the existing gas net. But of course, there are also other potential conflicts, for example, as this gas net could also be used to produce power to gas or hydrogen. So there we really need a combined strategy to address CO2 demand and sources and build up the necessary infrastructure. The German steel industry also has a very special role in the transformation of the industry sector because it's central in ramping up the hydrogen market. And in Germany currently there are various announcements of the different companies that around 15 billion euro investment will take place to hopefully provide 10 million tons of crude steel production capacity via green hydrogen reduction in 2030. And there are some factors that at least let us hope that this really will be successful. On the one hand side, of course, there is already experience with this technology, but also this green hydrogen reduction or the combined use with natural gas really has the potential to provide flexibility for the energy system, to use natural gas when electricity prices are high, to use hydrogen when we have a lot of renewables in the system. But also we see that there are support programs coming to enable investment and that there is a market building for green steel, especially from the automotive industry. In addition, there is also this window of opportunity because there are upcoming modernizations in the steel industry, which should now be tackled by transferring the sector to green CO2 neutral production technologies. What we also see is that industry, however, is still in a very strong tension field between economic efficiency, now facing very high natural gas and electricity prices, security of supply with the limited availability, for example, of green hydrogen in the near future, and sustainability. So we see that there is still need for improvement and forward planning is really necessary. And here just some ideas, what are really relevant points for the industry sector in Germany. So we need instruments that support, for example, the early replacement of plants in the steam and hot water generation to push electrification here, But of course, we also have to increase the economic efficiency of electricity, which is currently not competitive with fossil sources and biomass, for example. What we also need is really a very strong and reliable CO2 price signal so that we can also get very CO2 intensive energy carriers like coal or fuel oil out of the system. But overall, of course, we also need to accelerate now the development and the deployment of CO2 neutral processes for steel, for chemicals, for non-metallic minerals. And as I said before, this will only be possible if we have the necessary investments in renewables, electrolyzer capacities, and also the necessary infrastructures. And last but not least, of course, there also need to be a market for these products and also a possibility to give these CO2 price signals along the value chain to the end consumers. One possibility to do this could be, for example, the establishment of green lead markets. And with this, I give you only a very short introduction in what we do in our system analysis project, and I'm looking forward to your questions. Thanks.
Thank you, Andrea, for that insights. I think that was a perfect wrap up on potential and challenges, especially for the German perspective. It was quite impressive to see this order of magnitude and the needed investments related to that will be really huge and significant to give that transformation a chance. Are there questions related to that first contribution? We have time for 2 or 3 questions.
So, could I just ask my question or any procedure?
Yes, you are welcome.
Thank you.
Thank you.
So I was listening regarding the CO2 demand pretty carefully. And I wanted to ask what's the current status regarding the legal side so that this CO2 is then really accountable for the credits, because I learned in a project last year that this is not that easy and straightforward as you could assume, let's say.
Yeah, I think that's a very good question. And unfortunately, I think it's not yet finally decided. I think currently there is a process in setting up a carbon management strategy in Germany, but how to define and balance the CO2 emissions then, and also to keep them in the loop, it's not yet decided. So I think this is still an ongoing process, which I think has to be done rather fast to allow the, for example, cement industry to invest now in these technologies, also in Germany, not only in Eastern Europe, for example. Yeah.
Okay, thank you.
Thank you for that question. I think that will be definitely a challenge to align also the legal framework towards those upcoming utilization options. Is there another question on the talk and the activities here? Yeah, Manuel Gomez, please.
Oh, hello. Oh, thanks for the presentation. Just a quick question. In terms of reusing existing pipelines for CO2 transport, are there any technical challenges? Are they fully compatible with existing network? Thank you.
I try to answer as best as I can. I think a partial transformation of the gas transport net for CO2 transport is possible, but we see that there is really strong competition because these are the same areas where we potentially will need hydrogen and power to gas. So if this really will be a viable option is uncertain. In addition, I think there are some challenges also concerning the technical characterization, but I think I'm not an expert on this, honestly, but I think it's doable. So there are no major barriers. It's maybe like checking ventiles or something, but overall it should be possible to use this pipeline network if available.
Thank you. thank you. With that, I would thank you again for your great insights on your work and the scenarios. And I would like to give a virtual applause to you and hand over to our next speaker. It's Kevin Rubenhorst from Ammonia Energy Association Europe. He will dive into decarbonization options for ammonia production. So Kevin, thanks for your talk.
Thank you so much for the invitation. So I will represent the Ammonia Energy Association, talking about decarbonization of ammonia production and what's currently happening over there. So a brief insight on the Ammonia Energy Association. So we are the industry association that advocates for the responsible use of ammonia in the sustainable energy economy. And what does that mean? That means that on the production side for ammonia synthesis, we need to decarbonize ammonia production. But on the demand side, if we use ammonia as an energy carrier, so basically as a zero carbon fuel or as a hydrogen carrier, then we also need to look into how that is most feasible. We are a growing organization since we started in 2018 to 2019 as a trade association. We've grown to almost 200 members, so that really shows the momentum that ammonia as an energy carrier has at the moment. Some highlights of the things that we've done in the past. So we are currently working on a low carbon ammonia certification scheme because at the moment it is very hard to distinguish with regards to carbon intensities of different molecules of ammonia. Because in the end, if you're going to use ammonia as a fuel or as a hydrogen carrier, every ammonia molecule is basically the same. However, the carbon footprint is not, and therefore we need a transparent methodology to account for the carbon intensity. Secondly, we've written the Innovation Outlook Renewable Ammonia, where I've been quite involved. This is a report that's openly available at the website of IRENA. So if you're interested, please have a look. And two ongoing projects that we have are ammonia as a maritime fuel, where we map all the projects that are ongoing in the maritime space, as well as a webinar series that we run monthly. And I also run the low carbon ammonia plants list, where we basically look at all the plants that have been announced for low carbon ammonia production. And next to that, I also run a monthly webinar series explaining some of the projects to have a deeper dive. So why ammonia? So on the right-hand side, what you see in the center is ammonia, so that's NH3. And you can produce that by reacting hydrogen, either from renewables with electrolysis, so from water, or from other sources, you produce hydrogen. So for instance, with a steam methane reformer or another way to produce hydrogen, and you combine it with nitrogen, you make ammonia. And as you see, in principle, an ammonia molecule does not have any CO2. So it basically means that if you were to decarbonize that, the hydrogen production, then basically you don't need any CO2 in the cycle unless you need CO2 downstream. Currently, ammonia is mainly used for fertilizer production, so that's about 80–85%. So part of it goes to urea, but you also have nitrate fertilizers, phosphate fertilizers. And because of that, ammonia is actually the second most produced chemical by mass in the world. So a lot of ammonia is produced. However, as already mentioned, a lot of it goes downstream to fertilizers, which means that most of the ammonia is already converted where it is produced, and only about 10% of the ammonia that's produced is actually traded around the world. And as you can see on the very right-hand side, so it is on the top, it is used for fertilizers, but it also finds applications for DeNOx at the moment, but also as a chemical precursor or for other chemical uses. But in the future, it might actually be used as an energy carrier. So for instance, as a maritime fuel, maybe for power generation, backup power generation. But it might also be used as a hydrogen carrier. So you crack the ammonia back to hydrogen and it can be fed to the gas grid. For instance, in Rotterdam, but also in Wilhelmshaven, some ammonia crackers have already been announced. So how is ammonia produced? So ammonia is produced from hydrogen and nitrogen. And currently about 185 million tons per year is produced. And if you look at the very bottom, you see the fossil pathways. So about 75% of ammonia is produced from natural gas or naphtha. basically all around the world except for China. And in China, the main pathway is coal-based ammonia production. If you go a little bit more to the top, so the fossil-based hydrogen production with reduced emissions, and first what you can do is carbon capture and storage of your fossil-based hydrogen productions to reduce your carbon footprint. But there are also other pathways you can think about, for instance, electrified steam methane reforming for hydrogen, but also novel technologies like methane pyrolysis, or you have byproduct hydrogen, for instance, from ethane crackers or from chlorine plants. So it's also possible. And if you go a bit more to the top even, you have nuclear power or renewable electricity, and you can couple that with water electrolysis and produce either nuclear hydrogen or renewable hydrogen. But you can also think about renewable hydrocarbons from biomass. So you could also use that in an existing natural gas-based ammonia production plant. But essentially what's very important here is that more than 90% of your energy input for producing ammonia is based on producing hydrogen. So hydrogen very much determines the carbon footprint of your ammonia. And another thing to keep in mind is that colors of ammonia, so basically green, blue, pink, gray, they are useful for discussions of how the ammonia is produced, but it is not equivalent to carbon footprint. Because depending on where you source your energy or electricity, it really determines in the end your carbon footprint. So for that, we need certification. When looking at decarbonizing ammonia production, we see that a lot of projects have been announced. So we keep a list of all these projects, and what you see here is the total capacity that is announced. And you see that the total is somewhere around 170 million tons per year. That's a lot. That's almost the same as the current ammonia production. It should be noted that this accounts for all the projects. So there are quite some projects which have just an announcement that they want to produce renewable ammonia or low carbon fossil based ammonia. However, there are quite some projects already that are starting initially with a few megawatts, a few tens of megawatts of renewable ammonia production. So that's quite interesting to see. So what are some of the drivers that we see? So in the EU, we have this ETS system. So basically, if you emit CO2, you're being taxed. And also CBAM. We see that the shipping industry will be fully introduced in the emission trading system by 2026, which immediately means that low carbon fuels for shipping in the EU become competitive with fossil alternatives like LNG and heavy fuel oil. So we can actually expect that the shipping market will be one of the early uptakers of ammonia. And also in the US, there is quite an aggressive package with the Inflation Reduction Act with $3 per kilogram of hydrogen for the lowest carbon emissions, and it really is a driver to decarbonize ammonia production. And also for existing ammonia production where you don't need CO2 downstream, they could actually do CCS, and the tax credit that you get for that now, so the $85 per ton CO2, that's actually competitive to put it into the ground versus emitting it. So these are quite some developments that make low carbon ammonia production quite competitive. So now I want to focus a little bit on renewable ammonia production. There's also a lot to say about low carbon fossil-based ammonia production with CCS, but due to time, I will focus on renewable ammonia production. So it's basically made from water and air. So what you see in the bottom is you have water, you do water electrolysis with renewable electricity, and then you get hydrogen and oxygen as a byproduct. Nitrogen is purified from air using an air separation unit. And when you combine these and you pressurize these, you go to a Haber-Bosch ammonia synthesis loop, and the product of that section is ammonia. So some of you might be thinking, oh, this is something new, renewable ammonia production, but actually this has been operational for more than 100 years. So the first renewable ammonia plant was started operation in 1921. And down here you see some quite large plants that have been operational over the years in Norway. So this is a plant, I think, in Rjukan, Norway, where electrolysis-based ammonia production has been operational with over 100 megawatts of installed electrolyzers. And back then, this was mainly based on hydropower. And one note here is also that this has been operational for 100 years, but most of these plants have actually shut down, mainly because fossil-based ammonia production with natural gas was just a lot cheaper. So it is not a matter of technology readiness level, it's more a matter of economics. But as we see these new legislations coming into place with taxes on CO2, so some penalties, we might see a resurgence of renewable ammonia production. So what you see here is actually the last of these old, as we say, electrolysis-based ammonia production plants. This one is located in Chile, relatively small plant with 35 megawatts of alkaline electrolyzers. They produce about 32 kilotons per annum of renewable ammonia. So in this case, it's connected to the grid, so no fluctuations. And recently they signed a new power purchase agreement where the electricity of this plant is 100% renewable sourced. So that is actually the last of the renewable ammonia plants based on hydropower that's still operational. But what we see now is a lot of movement in the renewable ammonia production from solar and from wind. And as you know, solar and wind are fluctuating. So this also means that there's a challenge to operate your ammonia plant in a fluctuating way. So you can do that based on either having a flexible ammonia loop or by having a storage buffer, for instance, for hydrogen storage, or maybe a small battery storage for your electricity. And typically in practice, it's a combination of both. But as this is not major technology yet, so the fluctuating ammonia production, what we expect to see in the coming years is that the scale of these plants will increase over every year. And by 2025, 2026, we expect the first world-scale renewable ammonia plants to come online. So what you see here on this graph is on the x-axis the time, so 2020 to 2030. And the y-axis, the logarithmic scale of low-carbon ammonia production capacity, where all these different dots are individual projects for renewable ammonia production. And the dotted line there is a world-scale natural gas-based ammonia plant. So you see that beyond 2025, 2026, you see world-scale renewable ammonia plants. And what are these based on? So what you see here is that most of the projects are actually based on solar and wind. So not just solar, not just wind, but actually the combination of both. And the reason for that is that if you have the right complementary solar and wind, you can basically have a high load factor for renewable electricity, which basically means that you can build a smaller electrolyzer, making the project more competitive. So there are a few projects I want to highlight before finishing off. So in Norway, where the grid is mainly based on hydropower, the fertilizer producer Yara, they will install 24 megawatts of PEM electrolysis by 2023, so partially decarbonizing their existing natural gas-based ammonia plant. And they are also looking into fully decarbonizing that. One project is actually already operational, so that's Puerto Llano, where Iberdrola is operating a renewable hydrogen plant based on 100 megawatt of solar PV, some battery storage, 20 megawatt of PEM electrolyzers, and they have high pressure hydrogen storage as well on site. So it's quite interesting to see quite a significant scale already of 20 megawatts of PEM electrolyzers producing renewable ammonia in 2022 for Fertiberia. If we look a bit more into the future, we look at islanded renewable ammonia plants at large scale. Then this is an example project. So in the NEOM project, where the goal is to have 4 gigawatts. So that's 4,000 megawatt of solar and wind installed, over 2 gigawatt of alkaline electrolyzers, and more than a million tons per annum of ammonia. And this is already quite big, noting that this is probably bigger than the current combined electrolysis installed in the world. But if we look even further into the future,
sorry to interrupt you, Kevin, just for the timekeeping,
yes,
please.
Last slide.
Try to finish. Perfect. Excellent.
Yes. So, and this is actually last slide. So what I want to show is that in the far future, project developers are also thinking about tens of gigawatts of projects. So really renewable energy hubs. So this is the Australian Renewable Energy Hub, where the goal is to have 26 gigawatts of solar and wind to produce almost 10 million tons of ammonia per annum. And this is really ammonia production as a hydrogen carrier and zero carbon fuel at oil and gas scale. With that, I'd like to thank you for your attention.
Thank you, Kevin. Thank you, Kevin, for that perfect overview of the overall topic and what's going on in this field of ammonia. For that, we unfortunately have not really the time for additional questions, but we have the contacts to you. So if anybody has additional questions, please just directly contact Kevin or via us that we can forward them. Thanks a lot. With that, I would like to already give over the word to Joshua Makepeace from University of Birmingham, diving into R&D in the field of ammonia for the future. Thank you. You are muted.
Yeah, hopefully
Perfect.
you can hear me
Thank
now.
you.
Great. Thank you very much for the chance to present today. As was just mentioned, my aim is to talk a little bit about the state of play in ammonia synthesis and decomposition research. So we've just had from Kevin a great overview of the larger landscape of ammonia decarbonisation and some of the potential associated with that transition. And what I'll try and do is focus on some of the key technological developments which might help accelerate that transition. So my name's Josh Makepeace, and I'm a researcher in ammonia synthesis and decomposition catalysis at the School of Chemistry at the University of Birmingham. So as Kevin just mentioned, it's important to highlight before I dive into the research that's going on in ammonia synthesis catalysis, that actually the vast majority of the greenhouse gas and energy footprint of ammonia production is associated with the hydrogen production method. So you might reasonably ask what the value of further research in ammonia synthesis catalysis is. Well, there's a fair point that the development of industrial scale catalysts for ammonia synthesis is a very mature process. So here we're looking at a timeline of key catalyst developments and their efficiency of those catalysts, which we take to mean the proportion of ammonia that you would expect to produce under the conditions stated here of temperature. And we can see that at high temperatures, industrial catalysts perform very well. And indeed, even at slightly lower temperatures, there's been a very positive trajectory in the ability of industrial catalysts to synthesize ammonia efficiently. But if we're to think about working with ammonia synthesis at milder conditions, which might be favorable for smaller scale or distributed ammonia production, then the story is quite different. So here we look at the performance of a number of research catalysts with temperature. And as we lower the temperature of the ammonia synthesis reaction, the performance of those catalysts drops off quite sharply. So if we're interested in enabling milder conditions ammonia synthesis, then development of new catalyst formulations still remains of relevance. One of the key limitations to the development of conventional transition metal-based catalysts has been explored through some really interesting computational work by Jens Norskov's group, which looks at predicting where the most active ammonia synthesis catalysts would be based on their interaction with nitrogen gas in particular. And what they find is that essentially development of conventional catalysts moves you up and down this line here, whereas the most active synthesis regime would be in this red region here. So we need to think about new catalyst paradigms that allow us to move off of this kind of restricted model of ammonia catalysis. How might we do that? Well, we've kind of charted some new directions that are occurring in ammonia catalyst research. So if we kind of consider this schematic here, we could think about the state of play in terms of industrial catalysts, where we've moved from first generation materials, which were just active metals for ammonia synthesis, to ones which include electronic and structural promoters that aid the catalyst to produce ammonia more rapidly. In the research area at the moment, we're seeing more nuanced models of catalysts being developed. So thinking about systems where the support is actually more intimately involved in the catalyst process, whether it be that it stores reactive species that might hinder the catalyst process or creates very strong binding with the catalyst itself. Really interestingly, there's been a recent move to look at multi-site catalysts where the activation of the nitrogen and hydrogen happens at different parts of the catalyst. And what that means is that you can really get away from that limitation to the speed at which the catalytic reaction can happen. So this is the kind of area, these are the areas where ammonia synthesis catalysts, in terms of thermal catalysts, are being developed. When we're about to hear a presentation which focuses on electrochemical ammonia synthesis, which is the other big area of research, which I won't focus on for that reason. I want to move quickly on to thinking about ammonia cracking and the catalysts associated with that, because it's a much less well understood process compared with synthesizing ammonia. And the reason for interest in ammonia cracking is because it has the potential to help unlock flexible end uses of green ammonia. So if we think about this spectrum of between ammonia and fully cracked ammonia into nitrogen and hydrogen, there are a lot of different end uses we could consider. So if we were to think about it principally using ammonia as a hydrogen carrier and think about completely decomposing it into hydrogen and nitrogen, that's required for PEM fuel cells, hydrogen fuel cells that are currently dominating in the market, but also thinking about feeding hydrogen into the gas grid. As Kevin mentioned, there are a number of projects actively looking at that kind of ammonia cracking. But we could think about ammonia hydrogen blends, where there are fuel cell technologies which are more tolerant to residual ammonia in the gas stream. Or indeed thinking about ammonia hydrogen mixtures for combustion applications, such as being considered for maritime fuel applications. And indeed, there are fuel cells, such as solid oxide fuel cells, which operate at very high temperatures and so might not require active ammonia cracking at all. So there's potential for this dynamic use of ammonia that could be enabled by ammonia cracking technology. And so I wanted to highlight the current status, because you can currently purchase ammonia cracking units based on heterogeneous catalysts where there's a metal that facilitates the decomposition of ammonia. However, those systems are primarily designed for reducing atmospheres in metallurgical applications. They've not been developed with energy users principally in mind. So they tend to operate at fairly small scale, up to around 1.5 tons of hydrogen produced per day, although there have historically been examples of larger ammonia cracking plants, principally associated with heavy water production. The temperatures at which these these kind of commercial systems operate are very high, and that's because they use a steam methane reforming catalyst that hasn't been optimized for ammonia cracking. They can be electrically heated or gas-fired, but don't tend to be kind of integrated units that use some of the cracked ammonia to heat the unit itself, and so require an external energy supply. And they also tend to be, particularly for the smaller systems, not terribly efficient. And finally, they produce low pressure hydrogen, which of course can be dealt with, but perhaps for some applications, there's interest in higher pressure hydrogen production. So what are the key things to think about if we're looking to develop ammonia cracking technology that's more suited to these kind of decarbonisation activities? So just to mention a few key facts about the ammonia cracking process. It's thermodynamically favorable above 190 degrees Celsius, so can in theory happen at much lower temperatures than the current units allow. But it is kinetically hindered, and so we need catalysts to help promote that process. The process requires a continual input of energy of around 45 kilojoules per mole of ammonia cracked, and that presents some challenges for reactor design. And as I said, that means then that we need an external heat source, which equates to around 12% of the energy content of the ammonia. A key thing to think about is also the residual level of ammonia because of ammonia's toxicity or its incompatibility with some end uses. So this is what we would expect the equilibrium ammonia concentration to be at different temperatures. And if we needed to hit the PEM fuel cell limit, we'd have to be at very high temperature or use some kind of purification approach. Conventional catalyst systems are based on really two main metal systems. So the commercial units that you'll see mostly use a nickel-based steam methane reforming catalyst, which requires this higher temperature of operation. But there's a lot of work looking at the use of ruthenium for lower temperature activity, although of course ruthenium is a very expensive metal and so needs to be used carefully. So in the research field, there's a real focus on cheaper and more active catalyst formulations, particularly thinking about iron or nickel-based ones and indeed non-transition metal alternatives. So some of the work that we've been involved in looks at developing metal amide and imide catalysts, which show very promising catalyst performance at lower temperature compared with ruthenium and nickel and iron. So there are some emerging opportunities for these kinds of materials. And indeed, some recent work looks at combining metals and metal amides and imides in this kind of two-site catalyst model that I mentioned for ammonia synthesis. Of course, with ammonia cracking, we need to think about also potentially purifying the gas stream. So we have ammonia, which could be problematic from a function perspective or indeed safety or environmental perspective. Nitrogen can dilute your hydrogen fuel stream and indeed needs to be controlled for PEM fuel cells. And NOx emissions are a key factor to consider with combustion-based applications. There are a lot of technologies that are being used for gas purification, whether it's traditional pressure swing absorption, ammonia sorbents, which can simply trap ammonia from the gas exhaust, or more sophisticated technology like gas selective membranes that selectively transport hydrogen for your application, or further catalytic treatments that can remove NOx or ammonia. But these are also under active consideration for ammonia cracking units. So I just want to highlight some of the key research and development goals in ammonia cracking before I finish. So of course, the cost of the delivered hydrogen is going to be a key driver in improving ammonia cracking efficiency. That comes down to ammonia catalyst developments, but also key aspects such as reactor design, which allow for optimal thermal management of this endothermic process, or integration of sorbents or membranes that purify the gas stream as part of the catalytic reactor. And we're increasingly going to see interest in integrating ammonia cracking with power generation, such as combustion units that can make use of the waste heat associated with combustion for cracking applications. And of course, high pressure cracking and intermittent operation. Intermittent operation, as Kevin mentioned, runs across ammonia synthesis and ammonia decomposition to ensure that these technologies can be effectively coupled with renewable electricity. So that was a very quick whistle-stop tour of ammonia synthesis and decomposition research, and of course, happy to answer any questions or take questions via email. But thanks very much for your attention.
Thank you, Joshua, for your pictures, insight, and description of a very complex topic, and also what is going to happen straightforward here, probably in the future, to accelerate the progress. Probably one very short question. 1, 2, 3. If this is not the case, then I would thank you again for this very nice presentation, and I would straightforward give the word to Michael Stoukidis from Aristotle University of Thessaloniki, and our colleague and
thank you,
helpful mate will share the screen. Thank you, Claire. Excellent.
In the next 10 minutes, I will try to present the progress in the electrochemical synthesis of ammonia using solid electrolyte cells. I'm Michael Stoukidis from the Aristotle University of Thessaloniki. And next, please. Okay, ammonia synthesis is of key importance for humanity in general. And we're talking about more than 150 million tons per year, where quite soon we will be reaching 200 million tons per year. It looks like an easy reaction, nitrogen and combining with hydrogen, but in fact it's not. It involves thermodynamics, kinetics, everything. And first of all, in terms of thermodynamics, we have 4 volumes of gases producing 2 volumes of ammonia. And therefore, conversion is limited by thermodynamics. We know that it's limited by thermodynamics, and therefore conversion increases with pressure. In terms of kinetics, we have an exothermic reaction, and therefore conversion decreases with temperature. And as it was mentioned before, the idea of going to very low temperature to achieve higher conversion is wrong, because the triple bond in the nitrogen molecules is one of the strongest in nature. It's very hard to break that double bond, and then you have to use high temperatures. So the trade-off solution in industry for the past 100 years was to use temperatures around between 400 and 500 degrees centigrade, and high pressures like 150 to 300 bars. Under these conditions, the conversion is of the order of 15%. Next, please. These are the main steps in an ammonia synthesis plant. Hydrogen has first to be produced. The cheapest source for many years has been natural gas. So we convert methane. We have first the methane steam reforming to produce hydrogen, and further hydrogen production via the water gas shift reaction. Once hydrogen is produced, then hydrogen has to undergo extreme purification, because trace amounts of pollutants poison the catalyst, the very sensitive ammonia synthesis catalyst. Once it's purified, then the synthesis gas has to be pressurized. All these steps are both energy and cost consuming. And finally, we have the reaction of hydrogen and nitrogen to produce ammonia. So the overall reaction is something you can see down there, which is actually, and in fact, in a real plant, the ratio of CO2 to ammonia is not 0.4, but it's actually higher, because methane is also used as a fuel in the plant. Next, please. As opposed to industry, plants can convert nitrogen into ammonia at ambient conditions. They've been doing that for thousands of years. The way they do it is using a metalloenzyme, nitrogenase, and nitrogen of the air reacts with protons and electrons to produce ammonia. So essentially, that's an electrochemical reaction. That's how the plants produce ammonia. Next, please. In an effort to imitate nature, ammonia synthesis was studied at ambient conditions in liquid electrolytes. But, next please. Success was limited because liquid electrolytes operate at low temperatures. And at low temperatures, reaction kinetics are too slow. So we do not have much success. Next, please. Hopefully, thank God, we had the discovery in the early 80s of solid state materials, high temp, that can operate as proton conductors at high temperatures. These are perovskite type materials, as you can see here. And using these materials, next, as you can see here, we were able to produce ammonia from hydrogen and nitrogen at atmospheric pressure and at temperatures I see here about 500 degrees or higher. The system is simple. You have a solid electrolyte. On one side, at the anode, you have the production of protons from hydrogen. At the cathode, protons react with nitrogen to produce ammonia. This is what started as was named solid-state ammonia synthesis. Since then, next please. You can see here the research works on electrochemical synthesis of ammonia in the past 20-25 years. You see there is an explosion in research on both, using both either high temperature proton conductors or low temperature proton conductors. And this in the next 10 years, 5-10 years, God knows how this bar will go up. Next, please. In the past 20 years, the two major problems in electrochemical synthesis of ammonia were identified as, first, how to increase the conductivity of the proton conductors. As you know, as you can see, protons is a reactant, and therefore the proton flux determines the rate of production. The second problem is the Faraday efficiency. Faraday efficiency is defined as the fraction of protons that are converted to ammonia. Why that fraction is not 1? That's because there is a more favorable reaction of two protons to combine and react with the electrons and produce gaseous hydrogen. So we have hydrogen evolution. Next, please. Now I would like to show you a recent work in our lab in which we tried to combine solid-state ammonia synthesis and methane steam reforming in one cell, as you can see here. At the anode side, at the left-hand side, we introduce methane steam mixtures, and there we have the reactions of methane steam reforming and water gas shift. We have the production of hydrogen, and hydrogen produces electrochemically pumped from the anode side to the cathode side, where nitrogen will react with protons to produce ammonia. With this system, we have several advantages, several interesting advantages. These are, first of all, you don't have to purify hydrogen, because the only species that can be conducted through the solid electrolyte wall is protons. So any impurities will remain at the anode side. The second is that by pumping protons to the cathode, we increase the conversion of the methane reactions. And so we increase the conversion into hydrogen. The third, the third is that the high pressure requirement in the typical Haber-Bosch process is reversed actually here, because at the cathode side, you have one gas of nitrogen producing two volumes of ammonia. So even at lower pressures, this reaction is favored. The fourth is, I don't mention it here, that CO2 that is produced at the left-hand side is separated from nitrogen. So that makes collection of CO2 much easier. Next, please. These are experimental results of the system that I just showed you before. At the left-hand side, we have methane conversion and CO2 selectivity. And at the right-hand side, at the cathode side, we have the ammonia rate of formation and Faraday efficiency. Instead of showing you more of this, I just summarize, next please, these results. At the anode, we have a methane conversion up to 70%, with the CO2 selectivity exceeding 99%. So essentially, we convert all methane into CO2. At the cathode, we have a reasonably high reaction rate of ammonia synthesis. And unfortunately, the Faraday efficiency is not high. At the steady state, it's about 5.5%. But next, please. In the picture that I see, that you can see here, we have combined the ammonia synthesis reactor that is on the top that I showed you before with a similar solid electrolyte cell, which, however, operates as a fuel cell. And what does it do? The unreacted hydrogen that appears at the cathode is burned as a fuel in the fuel cell, and that produces electricity, which we use in the top cell. So with this, using this kind of system, next please. We can compare here what are the CO2 emissions in the electrochemical Haber-Bosch process, which is the dotted lines, the circles, versus a highly efficient conventional Haber-Bosch process, which is the dotted line. With the Faraday efficiency exceeding 35%, about 35%, we produce much less CO2 per kilogram of ammonia produced. Next, please. And of course, you can ask, this workshop here is for decarbonization. If I say just reduce a little bit the CO2, maybe you're not satisfied. So I have a better picture for you, which is next. As you can see here, I'm showing you again our reactor. If you don't introduce methane at the left-hand side, at the anode, and you just use steam, you can do the same things. You can again run the reaction, you will produce protons, they will react, blah, blah, and you will have ammonia formed. Of course, that's not without paying any penalty. And the penalty is shown next. Okay, the left-hand side figure shows the total energy requirements per mole of ammonia. And the right-hand side is the electrical energy requirement per mole of ammonia. As you can see here, if you don't use methane and you just introduce steam, you are at the top line, the red line, which means that you have to spend to operate at least 1 volt higher voltage difference, which is converted into about 300 kilojoules per mole of ammonia. So, to summarize, if you want to get rid completely of methane, fine, do it, but you will spend more electrical energy. But you can do it. And I think that's the last one. I hope I kept my time. Thank you.
Thank you, Professor Stoukidis, for that insight on your research and the latest developments of solid electrolyte development. I think it's quite promising, and you also showed the problems that we probably still face. Is there a question related to Professor Stoukidis' talk? If this is not the case, I will share my screen on another slide. We will dive now into the coffee break. So giving you a refreshment for 10 minutes. We will be back at 20 minutes past 3, starting sharp. Thank you, and see you in 10 minutes. Thanks to the 4 speakers for their valuable contributions so far. Stay tuned for the next.